Okay, welcome to Robotics 1. In today's class, we are going to talk about forces. Our next topic is going to be on the dynamic analysis. So in today's class, what I want to do is I want to start with some basic preliminaries. So if you have a coordinate system and this is X, this is Y, you have a unit vector. This is the unit vector I. This is the unit vector J. Now say if you have forces, imagine that you have a force F that is making an angle theta. Please note this is a force. You have F of X, which is F cosine theta I, and F of Y is equal to F sine theta J. Now, when you apply conditions of equilibrium, the conditions of equilibrium are for an object to be in equilibrium. So I will write these conditions down. Conditions of equilibrium. So summation of forces in the x direction is equal to 0. Summation of forces in y direction is equal to 0. Summation of moment about z is equal to 0 for the planar case. If you have a three-dimensional case, again, you will sum all the forces in x direction, y direction, and z direction and equate it to 0. You will find the moment about x, y, and z and equate it to 0. However, in this particular case, I'm interested in finding out the static forces on manipulator. So the question that I'm interested in answering is how to find static forces on robot. And then what is its relation to Jacobian? So in last class, I briefly mentioned something about virtual work. I mentioned about uh, virtual forces. So we will talk about virtual forces and we will try to see how does that affect the Jacobian and the joint torque. So let me set up the problem. So if you look at the problem, it's a two-link robot. So you have a two-link robot. And on this two-link robot, there is an external force, F, which is at angle theta, or say alpha. Now, what I want is, please understand, this robot has a motor here. There is a motor M1, there is a motor M2. Motor M1 is going to apply some torque. Motor M2 is going to apply some torque. So my question is, what should be the torque applied by motor 1 and what should be the torque applied by motor 2 so that this external force can be supported by the robot? And the application could be simple, that we want this robot to pick and place, or we want this robot to lift a weight, or we want this robot to grab something from point A and then take that object to point B, or we want this robot maybe just to hold something for a long period of time. So the question is, based on the robot geometry, in this static equilibrium position, what should be the values of the torque T1, T2, tau 1 and tau 2 to support external load? So the question that we are trying to solve is, given F, what are the values? What are tau 1 and tau 2? So first and foremost, what I need to do is I need to resolve this force in horizontal and vertical direction. So this force is F cosine alpha, and the vertical force is F sine alpha. So you have this force F that gets resolved, and let me add these angles for the sake of discussion. Let me say that this angle is theta 1, and what I'm going to do is I'm going to add this angle as theta 2. So I have this robot. The link lengths are L1 and L2, and there is external force F that is acting at the end of the second link, which is the end effector. So now, to solve this problem, I will have to separate out these links and draw the free body diagram. And please understand, this problem is super important because in this particular case, we are assuming that the robot is stationary. So the robot is stationary. But in the next chapter, we will have this robot moving, and we will have to derive the dynamical equations of motion. So this is the statics problem. So to solve the statics problem, I'm gonna draw the free body diagram of link 2. So consider link 2. Consider link 2. And the free body diagram means I will be freeing the link. So this is my link 2. This is my link 2. On this link 2, I have two forces. This is F of X, and this is F of Y. And then this link has been separated from the other link, which is over here. And as soon as I separate the links, virtual forces or reaction forces come in the picture. And I'm going to show the reaction forces here, something like this. So I have one reaction force here, and I have the other reaction force over here. And please note, these are the virtual forces. These forces came into existence because for analysis, we broke the joint, which means equal and opposite forces act on this joint. So these are the reaction forces, and these equal and opposite forces act on this joint. So I'm gonna just say this is my joint A and this is my joint B. So think about it, that here I have B of X and I have B of Y. and same forces, equal and opposite direction, would be acting over here, which are B of x and B of y. Please note that when this joint and this joint, they combine together, these internal forces, these are called as internal or virtual forces, internal forces, they disappear. Now this is length q, and the total angle with respect to horizontal. So please note, this angle is theta 1, this angle is theta 2. So the total angle that is made by this link with respect to the horizontal line is theta 1 plus theta 2. So that is the total angle. Now I'm going to write down the equations of equilibrium. Summation of forces in the x direction is equal to 0. So only forces in the x direction are f of x and b of x. So I would have f of x and b of x. So my equation is going to be b of x is equal to f of x. Please note, f of x is known, f of y is known. So b of x can be found out. Then the next equation is summation of f of y is equal to 0. And in this case, b of y is equal to f of y. In this case too, f of y is known. That means b of y can be found out. But here, one thing I want you to note is that this link is not fixed. Point B is a hinge. So this is a hinge. And there is a motor at that hinge. So the motor is going to apply torque. So I'm going to show torque here, and let me show it like this. So this is the torque given by this motor M2. So tau 2 is the torque given by motor M2. The total moment at point B is equal to 0. So I need to write down summation of moment about B is equal to 0. And please note, at this point, we are considering link 2. We are not at link 1. Link 1 is over here. So we are considering moment at point B. And the moment at point B is given because of fx, fy, bx, and by. So what I'm going to do is, I'm going to write down the equation for the moment. So summation, if you look at the moment, is 0 is equal to, I will have tau 2 plus f of x L2 sine theta 1 plus theta 2 minus fy L2 cosine theta 1 plus theta 2. Now, so I'm taking moment about point B. So moment given by f of x, if you curl your fingers in the direction of movement, your thumb is pointing towards positive z axis, which means that moment is positive. So fx, and I just want to show you this guy is L2 sine theta 1 plus theta 2, and this is L2 cosine theta 1 plus theta 2. But if you look at the moment given by f of y, curl your fingers in the direction of moment about B. the moment is about B. So the moment given by f of y is like this. So this is the moment of f of y. And if you look at the moment of f of x, this is the moment of f of x. So with all this information, now we have an expression for tau 2. Tau 2 is equal to fx L2 sine theta 1 plus theta 2 minus fy L2 cosine theta 1 plus theta 2. Gray writing, yeah, gray writing is, I wanted it to be very light because this is just for your reference. Can you see now? That is just showing you the direction of the moment. So consider point B. If you look at how this f of x is rotating about point B, can you see f of x is rotating counterclockwise about point B, and f of y is rotating clockwise about point B. Bx for link 1. Okay, we are not to the link 1 yet. So let me finish link 2 first. So hold on. So everyone understood the free body diagram of link 2 and the forces that I have found out for link 2. Any questions here? So now we have analyzed link 2. From link 2, we got these three relationships. This is equation 1, this is equation 2, and this is equation 3. These three are super important equations. Now let's move on to link 1. Now link 1, which is the dashed link, please note, I made a mistake earlier. So the leftward force is Bx on link 1. Downward force is By on link 1. So which means when this joint B is connected, when link 1 and link 2, they get joined, the red By cancels green By, and red Bx cancels green Bx. And since these are internal forces, they disappear. However, please understand that we know the values of Bx and By already. We know Bx is equal to Fx and By is equal to Fy. One thing that I did not draw, which I have to draw, is look at the torque. So this torque, tau 2, is acting counterclockwise on link 2. Once again, tau 2 is this torque is acting counterclockwise on link 2. This again is an internal torque, which means tau 2 would be acting tau 2 would be acting clockwise on link 1. That is super important. So please note that this torque is the reaction torque. And this torque is tau 2 acting on link 1, reaction torque on link 1. Now with this information, we are ready to solve link 1. So I'm going to draw the free body diagram of link 1. So consider link 1. The free body diagram of link 1 so this is L1. Now here I have the forces, and please note these forces are B of y, which is nothing but F of y, and this force is B of x, which is nothing but F of x, and I have a clockwise torque. I have a clockwise torque, which is tau 2. And we already derived the equation for tau 2. Since this link is separated from the hinge, which is at point A, so point A again was a hinge, you also have reaction forces, and I'm gonna show them over here. You will have A of x, you will have A of y, and equal and opposite forces over here, A of y and A of x. Again, these are internal forces. And let's not forget that there is external torque that is applied by the motor. So this is tau 1. So on this link, you have B is the joint, and joint B is shared. Joint B is shared by link 1 and link 2. So joint B is shared by link 1 and link 2. So let me show you that you have another link over here, and on this link you have, this is link 2, and you have by, and then you have bx, but you have, and I will draw it with a different color, external torque tau 2. And link 2, this link we already solved. Is the force acting on the joint. Yes, so there is reaction force acting on joint B, and there is force acting on, so this is the force on link 2, and you have the force on link 1. But please note, as joint B gets combined, which means link 1 and link 2 gets connected at joint 2, BYs cancel each other, the torques, they cancel each other. So what I need to do now is, for link number 1, consider the free body diagram, which is drawn over here. Apply summation of forces in the x direction is equal to 0. Summation of forces in the y direction is equal to 0. So for link 1, summation of forces in x direction is equal to 0. That tells me AX is equal to BX. In other words, AX is equal to F of X. This is equation 4. Then I have equation summation of forces in the y direction is equal to 0. That means A of y is equal to B of y is equal to F of y. In other words, A of y is equal to F of y. This is equation 5. Now comes the tricky part. Summation of moment, and I want you to understand this very carefully. Summation of moment at A is equal to 0. So when I say summation of moment at A is equal to 0, I need to take the moment of AX, AY. Since these forces AX and AY pass through the joint A, the moment given by these forces are going to be 0. However, there is torque tau 1. But this tau 1, if you curl your fingers in the direction of tau 1, your thumb is going out of the board, which means this tau 1 is positive. So please note this tau 1 is positive. Now, then what I have to do is I have one more torque, which is tau 2. But look at tau 2. Curl your fingers in the direction of tau 2. And I want you to be absolutely clear. The tau 2 is this torque, because now we are considering link 1, not link 2. So tau 2, if you curl your fingers in the direction of tau 2, it is in the opposite z direction. So now you have minus tau 2. And then look at the forces. You have f of x and f of y. Look at the forces, and I would highlight those for you. F of x and f of y. These are the forces. Let's look at the moments given by forces. Please note that this angle is theta 1. This angle is theta 1. This angle is theta 1. So this force Fx and Fy is going to give you moment, and these moments are F of x L1 sine theta 1 minus F of y L1 cosine theta 1. So take the moment of f of x and f of y. So this is f of y and f of x. And when you take the moment of f of x and f of y, in this particular problem, they are not. But if you have additional forces, they could be. So in this problem, the way the problem is set up, there are no additional forces anywhere on any other link. The only force is F, that is on the end effector. That's why that force is getting propagated all the way to the base joint. So now you have this equation 6. Now, if you recollect, we have 6 equations and we have 6 unknowns. So ax, ay, bx, by, tau 1, tau 2. So we can tau. So that is how you would get the forces. Now the next question is, and Jade, I will try to answer your question in just a second. Let me finish this discussion. Now I want you to look at these two equations very carefully. I want you to look at, so consider equation 3 and 6. Consider equation 3 and 6. What I'm going to do is, I'm going to rewrite these equations slightly. So look at equation 3. Equation 3 is 0 is equal to tau 1 plus. So I have tau 1 minus, I'm gonna substitute the values of tau 1 and tau 2. What you will see is you would have an equation for tau 1 and tau 2. You will have equation for f of x, f of y. So you would have tau 1 minus tau 2 is nothing but minus f of x L2 sine theta 1 plus theta 2 plus Fy L2 cosine theta 1 plus theta 2 plus f of x L1 sine theta 1 minus Fy L1 cosine theta 1. So this is the expression that we got. The earlier expression that we had, and I will write it down again just for the reference, was 0 is equal to tau 2 plus f of x L2 sine theta 1 plus theta 2 minus Fy L2 cosine theta 1 plus theta 2. So I want you to understand what happened here. In previous equation, consider this equation 3. From equation 3, we can get the values of tau 2. So we can find out what is tau 2. Tau 2 is equal to minus f of x L2 sine theta 1 plus theta 2 minus Fy L2 cosine theta 1 plus theta 2. This tau 2 we substituted in here. So we substituted tau 2 substituted from equation 3. And when we substitute tau 2 from equation 3, we have this equation 7, and this is equation 3 that is repeated over here. Now I want you to understand what is happening. You have a very nice expression for tau 1 and tau 2 in terms of fx and fy. So check this out, and I will repeat this once again. So you have tau 2, you have tau 1. Now these can be expressed in terms of fx and fy, fx and fy, fx and fy. So I could write this entire expression in terms of a matrix equation. And please follow what I'm doing here. I can write this equation down, and for the sake of simplicity, I'm going to write this equation down something like this. Tau 1, tau 2, and I would have a negative sign is equal to, I'm going to have a big matrix over here, and I'm going to have f of x and f of y. I'm going to have f of x and f of y. Now, what I would do is I would pick up the terms. So the terms that will be picked up are L2 sine theta 1 plus theta 2. That comes from the first term, plus L1 sine theta 1. Then I would add the term L2 cosine theta 1 plus theta 2 minus L1 cosine theta 1. So I will just make it L1 theta 1. So this, and here I'm going to have f of x and I'm going to have f of y. So what I'm doing is I'm rewriting equation 7 and equation 3 as a matrix vector equation. So now let's try to do the next same thing for the other problem. This equation will now become L2 sine theta 1 plus theta 2, and this equation will become minus L2 cosine theta 1 plus theta 2. Are you with me so far? So what we did here, we wrote, we converted. So this is, we wrote equation 3 and 7 in matrix vector form. And let's not forget that we have a negative sign over here. And this negative sign I just used to make it look more convenient. I'm going to take this negative sign from the left hand side, and I'm just going to move this onto the right hand side. So right now I have this equation, and what this equation does, and this argument is super important, this equation relates tau 1 matrix and F. So this is tau, and then you have this matrix. So what does this mean? This equation is relating external forces to the joint torques, and this equation is super important. Now this matrix that we have over here, okay, this matrix that we have over here, this matrix, can someone tell me what is this matrix? Correct. This is the Jacobian transpose. And what is the physical interpretation of this? I want to tell you the physical interpretation. So what is the physical interpretation? Now consider that you have a super complex robot arm. And when I say a super complex robot arm, that super complex robot arm may have multiple links. It has revolute and prismatic joints and a very complicated shape. I2C, L2C cosine. Which one are we talking about? Which term? L2, top right. L2, yes. Yes. Fx, let me see, this negative sign, this becomes positive. L1, so this will become negative. This will become negative. Then Fy, L2 cosine theta 1 plus theta 2 is negative. And then L1 cosine theta 1 plus theta 2 is positive. Okay. Oh, yeah. Sorry. Okay. Yep. So let me correct my mistake. Just a second. L2 sine theta 1 theta 2. First, let me add this over here. Fx L1. So this is positive. Then L2 cosine, yeah, this is negative, and this guy is negative. Okay. Yes. So and now is this equation look okay? Okay, fantastic. So here is the physical interpretation. Now imagine that you have a very complicated force here, F. And this force could be either supporting the load, or maybe supporting a paint gun, or maybe a pick and place, or it could be a very slow motion, which means the dynamical effects are not significant. So you want that robot to hold this weight for some time and then go to some different position and hold the weight there. The key idea is it's an open link, it's an open chain, which means you do not have any control over any other links. So that means you cannot add a support over here. You cannot say, hey, I'm going to add a support over here, I'm going to add a support over here, and so that this external load can be cancelled out. No, these supports are not possible. So the only thing that is possible for us is we have a motor here, M1, we have a motor here, M2, and we have a motor here, M3. So these motors, M1, M2, and M3, will not exert forces, but they will exert torques. So you need this M1 will say give you torque 1, this M2 will give you torque 2, this M3 will give you torque 3. So the question is, what is the value of tau 1? What should be tau 1? What should be tau 2? And what should be tau 3 to support F? And the answer, what the motor needs, yes. And so what that means is uh, what should be the holding torque, what should be the motor should be able to apply those torques. There is a slight difference between application of torque and holding torque, and I will get to it in just a second. So the idea is, if I give you the value of F based on the Jacobian, you should be able to tell me the values of torques. And the equation is this. Uh, Let me derive the equation, and then I'll tell you how it is interpreted. So all this comes from something called as the method of virtual work. And what is this method of virtual work? Which means if you consider the small teeny tiny displacement by the force, so assume that this force is displaced by teeny tiny amount, which is called as delta x. This teeny tiny amount of displacement multiplied by the force is going to give you work. So the work is equal to F dot delta x. Please note, work is a scalar quantity. Now, since there is nothing else, energy cannot be created, not can be destroyed, it can only change form. So which means this virtual work done by the force has to be equal to the virtual work dissipated or virtual work done by the motor. So this is work done by force. And work done by motor is equal to tau multiplied by delta theta. So this is work by motor. So you have work done by force, and on the other side you have work done by motor. By definition, F dx is equal to tau d theta. This is an important relationship. Now what I'm going to do is, since we are looking at a vector relationship, my F is actually a force which is something like F1. So for the sake of simplicity, let me say it is like F of X, F of Y, F of Z. This is the force in 3 dimensions. So I'm going to write this down as F transpose delta X. And what I mean by delta X is delta X is the displacement in the X direction, displacement in the Y direction, displacement in the z direction. So I have a force vector and I have a displacement vector. And I'm interested in taking the dot product, and the way the dot product is done is something like f of f transpose delta x. And I will write this down for a second. So which means f of x, f of y, f of z, delta x, delta y, delta z. So your total virtual work done is f of x delta x plus f of y delta y plus f of z delta z. So I would write this equation down as something like tau transpose d theta, because tau t is also a vector. Now, please note, we know delta x is equal to Jacobian delta theta. And that's what we did again and again. So what we do here is we substitute f or f transpose delta x as Jacobian delta theta is equal to tau transpose uh, delta theta. And now I can cancel out delta theta, delta theta. Now please note, I want this to be in slightly nicer format. So what I'm going to do is I'm going to take transpose on both sides. So I will have F transpose J. I will take the transpose of the whole thing. Tau transpose. I will take transpose of the matrix. So I'm taking the transpose on both sides. Please note this identity. If you have a matrix AB, if you want to take the transpose, it is B transpose A transpose. So if you have a product of a matrix AB, A is a matrix, B is a matrix, and you want to take the transpose of this product A times B, the answer is B transpose A transpose. This comes from the linear algebra. This is an important identity, so please remember. Perhaps you studied this in linear algebra, but this is what we are using. So now what I will have is, I will have J transpose, F transpose transpose is equal to transpose of a transpose is the vector itself. So A transpose transpose is A. So which means I have tau over here, and this means J transpose F is equal to tau. Now, what I'm going to do is I'm going to use a quick and dirty way to find out the Jacobian. Okay. So before I proceed further, everyone understood what we did. So let me quickly do a quick recap. So we have a robotic manipulator. On this robotic manipulator, we have an external force F. Please note this actuator, this manipulator is not moving. But what I want to find out is what are the joint torques. So what are the torques that are given by the motors? Now this needs a little discussion. Imagine if you have a DC motor, then you will have to continuously apply torque so that the DC motor holds that torque position. If you have a stepper motor, then you have to make sure that you energize the coils so that the stepper motor is capable of supporting that torque. So depending upon what type of motor you use, you have to make sure that either the torque, the torque value is the holding torque or torque value is the continuously applied torque. Now, based on the external force, we did the static force analysis and found out the values of tau 1 and tau 2. And these are the torques that need to be given by the motor. We used the conditions of static equilibrium and then found out that tau 1 and tau 2 are related to Fx and Fy by this matrix. And this matrix I'm saying is same as transpose of the Jacobian. And you seem to trust me, but I don't want you to trust me. Let me work out this problem real quick and let's find out the Jacobian. So I'm going to draw the kinematic diagram for the same robot. So you have this link, and then there is another link. Then this length is L1, this length is L2, then this angle, so angle here is theta 1, angle here is theta 2, this is my end effector. So my kinematic diagram is going to look something like this. And please note that this distance is 0. This distance is approximately 0. This distance is approximately 0. And what I'm going to do is I'm going to add my coordinate frames x0, z0. Again, I will have z1, x1, and I will have z2, I will have x2. Then I will have all the y's, y0, y1, and y2. Now, this is my end effector. This is my end effector. I want to find out the position of the end effector. And please note that you can actually rewrite the homogeneous transformation matrices or direction cosine matrices. We worked out this problem using the direction cosine matrices and Danavet-Hartenberg parameters. But at the end, the relationship that we obtained is Px is equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. Py is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And if I want to find out the Jacobian, what I need to do is I need to differentiate this equation and then find out what is the value of delta px. So I will differentiate the first term and I would have dpx is equal to minus L1 sine theta 1 delta theta 1 minus L2 sine theta 1 plus theta 2 delta theta 1 minus L2 sine theta 1 plus theta 2 delta theta 2. So this is the derivative of the first term. Then next term is delta dpy is equal to L1 cosine theta 1 delta theta 1 plus L2 sine uh, cosine theta 1 plus theta 2 delta theta 1 plus L2 cosine theta 1 plus theta 2 delta theta 2. Now what I need to do is I need to write this equation down as something like this. dpx dpy is equal to, this expression is going to become minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2 minus L2 sine theta 1 plus theta 2. This equation is going to look like L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And this expression is going to look like L2 cosine theta 1 plus theta 2. And here I have delta theta 1 and delta theta 2. So my Jacobian is this guy. Now I want you to check if the term that we have here, if this is Jacobian transpose. So let's look at the terms which are on the diagonal. Minus L1 sine theta 1 minus L2 sine theta 1 theta 2. So minus L1 sine theta 1 minus L2 sine theta 1 theta 2. So we have this term, we have this term. Let's look at the second row, second column, wherein I have L2 cosine theta 1 theta 2. Let's look at the term here. I have minus sine and minus sine, so this becomes L2 sine cosine theta 1 plus theta 2. But off diagonal term, because we are transposing, should get flipped. So let's look at the term L1 cosine theta 1 L2. So we are looking at this term. And if you go back, this term is here. If you look at this term is here. Don't forget that there is a negative sign behind on the left hand side of this matrix. So indeed, we find out that once we solve this problem, we get the Jacobian transpose. Shouldn't be L2. Did I make a mistake somewhere? Which term? L2 sine. Yeah, L2 sine theta 1, theta 2, px. Green part, top right. L2 sine sine theta 1, oh, L2 sine theta 1, theta 2. L1 sine. I delta. Okay, I don't know what term we are talking about. It's supposed to be cos. Which term is supposed to be cos? L1 sine, L1 sine, L1 sine theta 1, L1 sine, L1 sine theta 1, theta 2, L1 cosine theta 1, theta 2, L1, L2 cosine theta 1, theta 2, green part, top right. This term, L2 sine theta 1, theta 2, L2 sine theta 1, theta 2, 2 sine theta, L2 sine theta 1, theta 2, delta theta 2. So, okay, I'm going to highlight. Are we talking about this term? So, what about it? Okay. All right. I think it's right. I don't know what the confusion is. I mean, if you look at our Jacobian also matches, no? Oh, yeah. I have unmuted you, Trent.
Okay, so L2 sine theta 1 plus theta 2. Surely that should derive as cosine theta 2 at the far top right there.
L2 sine theta 1, theta 2. It's
Well,
a
what?
bracket. It's not a cosine. It's a bracket. This is this.
No, I'm talking about the far right portion of it. Is supposed to be sine or cosine there. Because the bottom below it, you switch the intervals. So I'm just trying to figure that out. Yeah, it's delta.
Yeah, it's delta, right? So,
Oh, it's delta. Oh, okay. That's what I thought it was sine for some odd reason. Okay.
okay. Good, good, good. Okay, this is delta.
I'll just mute myself.
Okay. Okay. Uh, yeah, it's not sine. This is delta. This is delta. This is delta. And this is delta. This is delta. This is delta. Okay. Good, good. Any other questions? So that is the power of the Jacobian. Now, what it means is once you have the Jacobian, you can find out the forces at any equilibrium condition. So now what I want you to visualize is imagine that you have a robot that is very slowly moving an object from point A to point B. So it's sort of a quasi-static, the same term that you see in thermodynamics. So if you can find out the torques at those quasi-static position, then you are able to perform the pick and place operation from point A to point B. And that is the biggest advantage of Jacobian. So with Jacobian, you are able to solve the problems uh, wherein external forces are given to you, and then you have to find out the torques. Okay, now what I want to do is, if there are no questions, I just want to give you some hints on the quiz. So please note that the quiz is due on 20th. So once again, quiz due on 10/20. So quiz 2 due 10/20. Now let's look at the first problem. So problem 1. So what you have is, I'm gonna uh, kind of try to draw the diagram, and again you are welcome to write your own assumptions, and then draw the kinematic diagram. And then, but please note that your forward and inverse kinematics should be derived based on the kinematic diagram that you draw. So if you look at this sketch that is shown in the quiz, this sketch is something like this. And then here that you have an end effector. And if you see here, they show something like this. There is motion shown over here, there is motion shown over here, and there is motion shown over here. So if I want to draw the kinematic diagram, what I would do is I would draw the kinematic diagram assuming the robot to be an R P P R. So this robot will be considered as R P P R. And let me draw the kinematic diagram. So this kinematic diagram is going to look like this. So you have this revolute joint, and then this revolute joint has on top of it a prismatic joint, and I will draw the prismatic joint here. This revolute joint has a prismatic joint. This prismatic joint goes like this, and at the end of this prismatic joint there is another prismatic joint. So I will draw another prismatic joint, and this prismatic joint is something like this. And at the end of this prismatic joint, now you have a revolute joint. So this is what you have. So you have R, P, P, and R. This is the only thing I just want to be clear, that the so you can add your z axis. So this is going to be your z0, this z1, this is going to be z2, and this is going to be z, actually this will be z3, this will be z3, and then you will have a z4. And then you can solve the forward kinematics. And please note that you don't really have to use the exact same variables that are shown in the figure. You can, if you like, you can assume your variables to be like A1, D2, D3, and this would be theta 1, and this would be theta 3. So you can add something like this. Now that is absolutely correct. If you look at the diagram that is shown in the figure, they have added additional offsets. For example, if you look at, there is an offset L6, there is an offset, so this distance L8, but those offsets, you can consider approximate them to 0. That's totally fine. For example, L6, the offset between the two joints, you can approximate it to 0. That's totally fine. So what I'm trying to say here is, uh, so state the assumptions. So state assumptions. And so just I gone through one example wherein you have the robot and you have constructed the kinematic diagram, and these are the dimensions that you are using for your forward kinematics. So this is what you'll use for forward kinematics, and this is what you will use for your inverse kinematics. Would that be included? A1 diagram? Yeah, you can include that in the A1. So for an example, the question is, there is L3 and L4, right? So L3 and L4 would be your A1. So just draw a consistent kinematic diagram and state the assumptions. Yes, for DH table, you will have to show that. So let me tell you, when you do the DH tables, your intermediate homogeneous transformation matrices may not match. And this is something that you should keep in mind. So when you do with DH parameters, intermediate homogeneous transformations may not match. But your final will. Answer will. The only limitation of the DH parameter technique is if you have any dimension in Y direction, DH parameter technique would fail. So when you choose your coordinate systems, you should choose the coordinate systems wisely. And in certain cases, it is absolutely not possible to avoid dimension along the y-axis. So at that time, you would state that the DH parameter technique fails. So that is what you should keep in mind. The next problem actually is an interesting problem. Just to give you a hint, in problem 2, you have a revolute joint. So you have a revolute joint. Then this revolute joint is attached to another revolute joint. So this is a revolute joint, and this is another revolute joint. Now, then you have forward, and then you have a revolute joint which is at an angle. You have a revolute joint which is at an angle, and then you have another revolute joint which is at an angle. So this is the first revolute joint, this is the second revolute joint, this is the third revolute joint, this is the fourth revolute joint. So you have R, 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 R. Yes, to answer to John, yes. So the next thing that you want to be careful about is you want to have the distances, vertical and horizontal distances between these axes. So when you draw the diagram, you have to make sure that you are selecting the appropriate dimensions. Then the last problem is actually an easy problem. In last problem, you have a revolute joint, then you have another revolute joint, and then you have a prismatic joint, and this prismatic joint is attached to another revolute joint. So you have a revolute joint, you have a revolute joint, you have a prismatic joint, and you have a revolute joint. Now, nobody has stopped you from constructing this robot like this. This is the same robot, and this is similar to the problem that we have worked out in the class. Quiz 2 is 30 points. Okay. There is only two revolute joint. Where two revolute joint? Let me problem 3. Oh, RPR, RPR, RPR. Oh, yes, 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 yes. I made a mistake. I made a mistake. R, yes, I made a mistake. This is how it is. RPR. Yeah. Thanks for catching that. Yeah, RPR. This is how the robot is. RPR, RPR. Yes. Okay. Quiz 2, it's, in my opinion, is slightly involved. That's why it has 30 points. Because it's asking you to do a lot of stuff. It's asking you to do kinematic diagram, forward kinematics, forward kinematics with DH parameters. That's why quiz 2 is worth 30 points. Yes, Z axis has to be along the joint of rotation. So to answer your question, if I were to draw the Z axis, this would be my Z axis. This would be my Z axis. This would be my Z0. Z0, Z1, Z2, Z3, and then there will be a Z4. so it's worth 3 times a normal quiz. I didn't think of it that way, but I understand that this quiz is more work. That's why it has more points. All right, I'm gonna stop recording, but I would be here to answer the question.